University, and my presentation is called Dynamic Impact of Power Electronics Converted at the Grid Edge. According to the IPCC, global CO2 emissions need to be halved by 2030 to prevent severe climate change. Otherwise, disasters such as droughts, increased sea levels, wildfires will increase in severity. On the other hand, recent disasters around the world, like Hurricane Harvey in Houston and Hurricane Maria in Puerto Rico, have demonstrated that the grid is not resilient enough. Natural disasters are not the only cause of power interruptions. Just this year, an accident in Germany left 30,000 households and 2,000 businesses without electricity for more than 30 hours. So since electrical energy is vital for modern society, there is a need to restore all, or at least the most critical needs of access to electricity as fast as possible. A solution for this, governments around the world have been trying to increase renewable energy penetration, and solar PV generation is one of the fastest growing sources of renewables. And most of the new solar installations are being done at the distribution level. So according to the DOE, 30% renewable energy penetration is possible without doing significant changes to the electrical grid. But what if we want to go higher, like 54%, as this projection by the Department of Energy? Then the distribution level will need a huge increase in voltage regulation devices and control devices along the network. So to address this, we're proposing, addressing the step B of this conference, Power Electronics Intelligence at the Network Edge, or PINE for its initials. This is a power electronics topology that is connected just behind the electrical mirror, which is the very edge of the grid. It consists of three parts: the active rectifier that will draw, not sinusoidal, but with very minimal harmonics current from the grid. It will maintain a constant DC voltage here of 400 volts, and that will feed the output converter that will feed the typical residential American home of 240 volts split phase. It has also these advantages. It enables energy budgeting. So because it handles all the power that is drawn from the grid, it improves resilience. We can limit the amount of power that each house is consuming. It also enables peer-to-peer energy transactions between residential customers, allowing a more distributed decision-making. And because it handles the power that comes from the grid, it can maintain a constant voltage at the load of your house, even when there's variations on the voltage grid. So more research is needed to fully understand the physical impact that more power electronics into the grid will have to the grid. So in order to study this, we propose categorizing the main factors in these four categories, which is the modeling of loads, the control of the load, the network structure, and the power electronics design. So the modeling of loads is essential for voltage stability purposes, studies. It's basically grouped in two main categories: static and dynamic models. The static models express power as a function of voltage, and the dynamic models express the power as a function of voltage and time. So to show the difference, we have here two figures made by this paper for this, made by engineers from the Hokuriku Electric Power Company in Japan. They connected different loads to a generator to see what are the effects of a voltage disruption. So in here, after 0 seconds, they simulated a voltage drop, and we can see that the dynamic load goes out of synchrony, but the static load remains stable. And we can see here the impedance of the dynamic and the static load. We can see again the voltage drop is simulated here, and then after 70 milliseconds, the fault is cleared, and we can see that the dynamic load, it doesn't return to the initial value of the impedance, but the static load almost immediately goes back to a very similar value and stays there. So since we're claiming that PINE will have an output constant voltage, it will exhibit almost zero dynamics. So even if a dynamic load has to comply its algebraic and differential equations, it can still see it as a static load. So the next group is the control of the load. The loads are basically connected in two different ways. One is directly connected to the grid, The problem with this one is that they're susceptible to grid voltage variations. And the second way is the loads interfaced via power electronics. So these loads will have a perfect voltage at their input, but the problem is that they draw harmonics from the grid. So these harmonics along the grid may result in oscillations, which can be magnified by control of converters interfacing with the grid at different points of the grid, or parasitic capacitors of power cables. Since PINE can decouple the harmonics and the dynamics from the grid and the load, the stability will be improved. The next group is the network structure. To discuss this, we prepare a small test system with only 2 feeders. Each feeder is providing a PINE load for 5 kilowatts. Well, it's designed for 5 kilowatts, but we can see that if it's not properly designed, we simulated a voltage drop in the grid. So it's a voltage increase after 1 second. It increases by 15%. It's the PINE control maintains the voltage perfect, but then after 1.4 seconds, the voltage goes back to 1 per unit, and the system becomes unstable. But if we, again, adjust the control parameters of PINE, we can make it stable again. In this next simulation, I'm doing the same process. The voltage from the grid is increased 15% after 1 second, and then goes back to after 1.4 seconds. We can see that it's stable. But then at 1.6 seconds, a loss of line is simulated. And then we see again, we have a loss of stability. So the last part is the power electronics design. Again, if we don't properly control the power electronics, we will see an unstable case. But if we adjust the parameters, we will get a stable case again, because we successfully separate the dynamics from the grid and from the load. The converter, the most important part of any converter is the part that interfaces the whole topology with the grid. To talk more about the power electronics design, what do we mean by that? Power electronics design means the design of the input inductor, the DC link capacitor, the control of your active rectifier, or the control of your output inverter, the design of your filter, etc. So, but the most important part is the active rectifier. So to prove that, we did a small analysis design, again with a very similar test system, only 2 pines, 5 kilowatts each, only 2 feeders. An average model was developed, and each pine will have 22 states. So with 2 pines, we have 44 eigenvalues. Out of those, 24 eigenvalues are just real, only have real components, and 20 have complex components. So the main parameter that will affect stability is the load. If the power electronics is not properly designed and we increase the load from 5 kilowatts to 29 kilowatts, we can see we have a zoom in here. These eigenvalues will cross to the right half plane, making the system unstable. The next most delicate part is the design of the control of the input active rectifier. So it's basically controlled by a PI controller. So if we increase the proportional gain from 4.8 to 80, which is almost 20 times, again, the system will go unstable. The other parameter is the integral gain of the PI controller. Again, we have to increase it at like 10 times in order to make it unstable. So for the concluding remarks, PINE is a key enabler of 100% renewable vision for the future. The physical layer impact is investigated. We categorize the main aspects that could contribute to dynamic instability. And the mitigation of dynamics is possible through proper control of the power electronics. And for the future, we want to include more detailed systems for small signal analysis, which means more pines, more options for parts of the grid going to islanded mode, more opportunities to have loss of lines, dynamic loads, energy transactions between pines, etc. We are currently under preparation of a hardware implementation of Pine, and we're going to develop business model innovations enabled by this new topology. Thank you. Questions?
Yes. Yes, you. Yeah.
So with the renewables, the disturbances in general are going to be large in magnitude. So how would you support the small signal analysis that you've been conducting?
Oh, we need to increase the complexity of the grid. Can you repeat the question?
Small signal analysis going to be valid for large changes.
The changes we have done is 15% of the input voltage. So yeah, we need to increase the complexity of the whole model. But yeah.
I'm the co-author. So we do two steps. The first step is a small signal analysis. The second step is a transient analysis. And the small signal is actually continuously based upon the linearization of the changing operating conditions. So in that regard, I see both as necessary.
Thank you.
Yes, sir.
Yes. So I realize this study's not primarily an economic study, but do you have a sense about cost? Like, how different is the cost of an interface like this, a Pine interface, compared to an inverter that people would use now?
Basically, will double. And yeah, you can see that we have actually two inverters. So that's the main part that is going to contribute to the cost.
And a battery as well?
Well, the battery is the same the system as they was used before. We're just adding the input inverter.
Yeah,
so to speak.
Home systems don't use a battery.
Mm-hmm. Oh yeah, but yeah, we're comparing it with previous solar systems that has batteries. Yes.
Oh, yeah.
Just a short one, maybe on the losses. Can you comment a little bit on the differences in losses with this system versus conventional systems when you do the inverter?
Yeah, because we can handle the power that comes from the grid, we reduce the harmonics. So by reducing the harmonics, you reduce the total current from the grid. So that will reduce the losses.
Have you quantified that?
No, not yet. We haven't. We need to have a bigger system in order to.
It's an interesting one.
Yeah, our testbed analysis is being done with just 2 pines for now. Mm-hmm. But we are working on towards a system that will look more like a IEEE 37 node test feeder. So need more complexity.
Yeah, so you focus on the physical layer basically and the stability. So I'm curious, is there like an economic part of this as well, like how to send economic signals between components in this concept? I mean, similar to the previous presentation.
How do you optimize across multiple times? Is that kind of the question, using economic signals?
Yeah, that's right, yeah.
We haven't got to that part. We're
Maybe I could comment a little bit because this is a kind of a bigger project, and Jorge is doing one part which is focusing on the power electronics side.
Yeah.
But we have another big team working on enabling peer-to-peer transactions by this enabled Pine concept, and also related to the loss actually component. One thing we actually did study and publish is that we quantify the delivery loss part as well based on a typical Houston-based distribution system. So we see this as an enabling platform for innovative business models and concepts such as peer-to-peer transactions. Yeah.
Any other questions or comments? Great, thank you very much.